In multivariable calculus, we often encounter surfaces defined by two parameters, u and v. Today, we will learn how to calculate the total area of these curved surfaces by using the power of double integrals and vector geometry. While some surfaces can be written as functions of x and y, parametric equations allow us to describe complex shapes like spheres, tori, and cylinders more easily. This flexibility is essential for solving real-world engineering and physics problems. Every parametric surface is a mapping from a flat region in the UV plane to a curved shape in 3D space. To find the area of the curved shape, we must understand how the area of a small rectangle in D changes when mapped. To measure the surface, we look at the partial derivatives r_u and r_v. These vectors are tangent to the surface at any given point. They represent the rate of change of the surface position as we vary each parameter individually. The cross product of these tangent vectors gives us a normal vector. Crucially, the magnitude of this cross product represents the area of a tiny parallelogram on the surface corresponding to a tiny square in our parameter domain. This leads us to our fundamental formula. The surface area is the double integral over the domain D of the magnitude of the cross product of the partial derivatives. This magnitude acts as a local scaling factor for the area. To solve any problem, we follow 5 steps: define the vector function, find the partial derivatives, compute their cross product, find the magnitude of that result, and finally evaluate the double integral over the specified limits. Let's find the surface area of a cylinder. We parameterize it using the angle u and the height v. Our radius a is a constant. We will now calculate the derivatives to find the area element. First, we take the partial derivative with respect to u, which gives us the horizontal tangent. Then, we take the partial derivative with respect to v, which gives us the vertical component. Notice how simple these vectors are. Next, we compute the cross product. Setting up the matrix with our tangent vectors, we find the resulting vector is of a cosine u, a sine u, 0. This vector is always perpendicular to the cylinder's surface. Now we find the magnitude. Using the Pythagorean identity, the expression simplifies beautifully to just eta. This means the area scaling factor is constant everywhere on the cylinder, which makes sense given its uniform shape. Let's look at a cone. This time, our parameters are r and theta. As r increases, the circle expands and moves upward, creating the cone shape. Let's see how the magnitude calculation changes here. After calculating the cross product and magnitude, we find the factor is a times the square root of 2. Unlike the cylinder, our scaling factor depends on the radius, because the cone gets wider as we go up. Choosing the right parametrization is half the battle. For spheres, use spherical angles. For flat planes, standard x and y coordinates work best. For surfaces of revolution, use the axis of rotation as one of your parameters. To summarize, the magnitude of the cross product of tangent vectors tells us how much the area is stretched or compressed. Integrating this value over your parameter domain gives the total surface area. Here is a quick question: if the magnitude of the cross product is exactly 1 everywhere, what is the surface area? The answer is A. It is simply the area of the domain D, because no stretching occurred during the mapping. You are now equipped to calculate the area of any parametric surface. Practice with different shapes to become comfortable with the vector cross products. Thank you for watching. Generated by Vision Solve AI.